Hi everyone! Welcome to another lesson in general chemistry. For today's topic, we're going to discuss Avogadro's number and the mole concept. Let's begin. Avogadro's number will start with the study of stoichiometry. When we talk about stoichiometry, this refers to the quantitative relationship between the substances that are used up and produced in a chemical reaction. For example, we have combustion of methane. And here, our reactants are methane and two molecules of oxygen. When combustion happened, it will yield up a molecule of carbon dioxide and two water molecules. When studying stoichiometry, you will also have to deal with Avogadro's number. So, what is Avogadro's number? It is certainly easy to count bananas or to count elephants, as long as you stay out of their way. However, you would be counting grains of sugar from your sugar canister for a long time. Like those, atoms and molecules are extremely small, far smaller than grains of sugar. Counting atoms or molecules is not only unwise, it is absolutely impossible. For example, one drop of water contains about 10 to the 22nd power molecules of water. If you counted 10 molecules every second for 50 years without stopping, you would have counted only 1.6 nonillion molecules. Put another way, at a counting rate, it would take you over 30 trillion years to count the water molecules in one tiny drop. So because of this, chemists needed a name that can stand for a very large number of items. Amadeo Avogadro, an Italian physicist and lawyer, provided such a number. He is responsible for the counting unit of measure called the mole. A mole is the amount of substance that contains about 6.022 times 10 to the 23rd power representative particles of that substance. The mole is the SI unit for the amount of substance. Just like the dozen and the gross, it is a name that stands for a number. There are therefore 6.022 times 10 to the 23rd power water molecules in 1 mole of water molecules. There also would be 6.022 times 10 raised to the 23rd power bananas in 1 mole of bananas. So if such number of bananas ever existed. Ayan. So Avogadro's number will also revolve around representative particles. And what are representative particles? This refers to the species present in a particular substance. This is also the smallest unit in which a substance naturally exists. It can be in a form of atoms, molecules, ions, or formula units. The representative particle of most element is the atom. For example, copper and mercury have copper and mercury atoms respectively. For majority of the elements, the representative particle is the atom. However, 7 elements exist in nature as diatomic molecules. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. For you to better remember the 7 elements, you may need to remember this mnemonic. Have no fear of ice-cold beer. Have for hydrogen, no for nitrogen, fear for fluorine, off for oxygen, ice for iodine, C for chlorine, and B for bromine. So the representative of these elements and all of the molecular compounds is the molecule. Now, How do we calculate the number of representative particles using the conversion factor? So the formula would be number of representative particles equals the number of moles multiplied to the Avogadro's number, which is 6.022 times 10 raised to 23rd power representative particles over 1 mole. Now, let's have sample problems regarding the computation of these representative particles. For example, we have problem number 1. How many particles are there in 5.50 moles of glucose? So first, we have to determine what is the representative particle. Is it an atom? Is it an ion? Is it a molecule? Or is it a formula unit? So glucose is a molecule. Therefore, we're going to write number of molecules equals the number of moles. So the number of moles would be 5.50 moles of glucose multiplied to the Avogadro's number over 1 mole. So 5.50 moles of glucose times 6.022 times 10 raised to 23rd power representative particles over 1 mole. Now, let's cancel out the same units. So, we're going to cancel moles. So, 5.50 times 6.022 times 10 to the 23rd power, we'll be having an answer of 3.31 times 10 raised to 24 power glucose molecules. Ayan. Now, let's have another example. How many particles are there in 1.75 moles of aluminum? Now, the first thing that we have to do is to determine what is the representative particle. So we have aluminum. Since aluminum is not a diatomic molecule, therefore the representative particles of these is atom. Ayan. So the number of atoms is equal to the number of moles, which is 1.75, multiplied to the Avogadro's number over 1 mole. So we have 6.022 times 10 raised to 23rd power representative particle over 1 mole. We're going to cancel out the same units, which is the mole. So compute 1.75 times 6.022 times 10 raised to 23rd representative particles. And the answer would be 1.05 times 10 raised to 24 power aluminum atoms. Okay, now let's move on with the next problem. How many particles are there in 4.65 moles of copper? Since we're dealing with copper, representative particles are atoms. So the formula would be number of atoms equal to 4.65 moles of copper multiplied to the Avogadro's number over 1 mole. So 6.65 times 6.022 times 10 raised to 23rd power representative particles. We're going to cancel out the units. And the answer would be 2.80 times 10 raised to 24 power copper atoms. Now let's move on with molar mass. So what is molar mass? This is the mass of 1 mole of a pure substance. How do we compute for molar mass? For example, what is the molar mass of magnesium? So this time you're going to need your periodic table. Take a look at your periodic table and look for the atomic weight. Okay. Typically, the atomic weight is on the upper right corner or on the bottom corner of your periodic table. Ayan. So looking at the atomic weight or atomic mass for magnesium, we have 1 mole is equivalent to 24.31 grams of magnesium. Now let's have another problem involving molar mass. The question is, what is the molar mass of nitrogen trichloride? So enable for us to compute for the molar mass, we have to look for the atomic weight of nitrogen and chlorine. So looking at your periodic table, nitrogen has 14.007, while chlorine has 35.453. Let's deduce our numbers into two decimal places. So nitrogen, how many atoms of nitrogen are there in nitrogen trichloride? We only have 1. Therefore, we have to multiply 1 times 14.01. So 1 times 14.01, we have 14.01 grams per mole. Now let's take a look on chlorine. We have 3 moles of chlorine. Therefore, 3 times the atomic weight, which is 35.45, we'll get an answer of 106.35 grams per mole. Now let's add up this. So 14.01 plus 106.35 will get an answer of 120.36 grams per mole. Therefore, the molar mass for nitrogen trichloride is 120.36 grams per mole. So let's have sample problem number 3. Now, what is the molar mass of ferric oxide? Now again, we're going to look at our periodic table and look for the atomic weight of iron and oxygen. For iron, we have 55.845. And for oxygen, we have 15.999. Again, we're going to deduce our numbers into two decimal places. Therefore, if we're going to look at the formula, we have Fe2O3. So this subscript symbolizes the number of atoms present for each element. So we have 2 atoms of iron, therefore, this would be 2 times 55.85. So 2 times 55.85 will get an answer of 111.70 grams per mole. Now let's solve for oxygen. Oxygen has 3 atoms. So 3 times the atomic weight, which is 16. So 3 times 16 is 48 grams per mole. Adding up, 111.70 times plus 48 will get an answer of 159.70 grams per mole. Therefore, the molar mass for ferric oxide is 159.70 grams per mole. Okay, now let's move on with the mole concept. The mole concept is the summation of the Avogadro's number, the molar mass, the molecular mass, and the formula mass. Okay, sample problem. In a 5 gram of ferric oxide, compute for the following. A. Moles of ferric oxide. B. Particles of ferric oxide. C. Moles of iron. And D. Ions of iron. Now let's start off with letter A. We're going to calculate the number of moles of ferric oxide. Enable for us to do that, again, we're going to get the molar mass first. So earlier, we've already computed the molar mass for ferric oxide, which is 159.70 grams per mole. Now that we already got the molar mass for ferric oxide, let's continue with computing for the numbers of moles for ferric oxide. So the first thing that we have to do is to convert from grams to moles of a substance. In order to do that, we're going to get the number of grams in our sample, which is 5 grams of ferric oxide. Yan. Multiplied to our molar mass earlier, it states that in every 1 mole of ferric oxide, there are 159.70 grams. Now, let's cancel out the similar units which is the gram of ferric oxide, leading with 5 grams times 1 mole divided by 159.70. So I'm giving you time to compute for this, and the answer would be 0.0313 moles of ferric oxide. Okay, now let's move on with letter B. In every 5 grams of ferric oxide, how many particles are there? Earlier, we already got the number of moles. So, the formula would be the conversion from grams of a substance to its number of particles. So, earlier, the number of moles is 0.0313 moles of ferric oxide. Then we're going to multiply it to the Avogadro's number that states that in every 1 mole, there are about 6.022 times 10 raised to 23rd ferric oxide particles. Now, we're going to cancel out the similar units, which is the mole of ferric oxide, and we calculate 0.0313 multiplied to 6.022 times 10 raised to 23rd particles, and the answer would be 1.89 times 10 raised to 22nd power ferric oxide particles. Okay, now let's move on with letter C. In every 5 grams of ferric oxide, how many moles of iron are there? Able for us to calculate for this, we have to get the conversion from a mole of a compound to mole of its component particles. When we're talking about component particles, we're dealing with the elements that made up that specific compound. So in here, in every 1 mole of ferric oxide, or Fe2O3, there are 2 moles of iron. How do we get the number of moles? You can simply look on the subscript. So in here, the subscript for iron is 2, and the subscript for oxygen is 3. Therefore, there are 2 moles of iron and 3 moles of oxygen in 1 mole of ferric oxide. Now let's calculate. We already got the mole of the component particles, and earlier, we've calculated that 1 mole of ferric oxide is equivalent to 0.0313 moles multiplied to, in every 1 mole of ferric oxide, again, there are 2 moles of iron. So now, let's cancel out the similar units, which is mole for ferric oxide, and calculate. So 0.0313 times 2 moles divided by 1. And the answer would be 0.0626 moles of iron. Now let's move on with letter D. How many ions of iron are there in 5 grams sample of ferric oxide? Enable for us to get the number of ions, we have to get the conversion from grams to moles to particles. Again, from grams to moles to particles. So, our sample has 5 grams. So, write 5 grams. Multiplied to the number of moles. So, on our earlier computation, in every 1 mole of ferric oxide, there are about 159.70 grams of ferric oxide. Next, we're going to get the number of moles of iron. So, in every 1 mole of ferric oxide, there are 2 moles of iron. Again, where do we get the 2 moles? By looking at the subscript for ferric oxide, which is Fe2O3. This means that there are 2 moles of iron and 3 moles of oxygen. Going back, the next one is we're going to multiply this to the number of particles. So in every 1 mole of iron, we have 6.022 times 10 raised to 23rd power iron ions. Now let's cancel out the similar units. So we're going to cancel the grams, the number of moles, and the number of moles for iron. There you go. And calculate. So 5 times 1 times 2 times 6.022 times 10 raised to 23rd power divided by 159.70, and the answer would be 3.77 times 10 raised to 22nd power ions. Clear? Now let's move on with another problem for you to better understand how to get the different mole concepts. Okay, another practice problem. In every 7 grams of magnesium oxide, calculate the following. The first one, we have moles of magnesium oxide, the particles of magnesium oxide, the moles of oxygen, and the ions of oxygen. Again, the first step in getting the mole concept is to calculate for the molar mass. So what is the molar mass for magnesium oxide? Again, you're going to look at your periodic table and determine what is the atomic weight for magnesium and oxygen. And magnesium has 24.305 and oxygen has 15.999. Again, we're going to deduce this into 2 decimal places. So the equation would be magnesium has only 1 atom, therefore 1 times 24.30. And oxygen has only 1 atom as well, so 1 times 16. So 24.30 plus 16 will get an answer of 40.30 grams per mole. Therefore, the molar mass for magnesium oxide is 40.30 grams per mole. Now that we already got the molar mass, Now that we already got the molar mass for magnesium oxide, let's calculate the number of moles in every 7-gram sample. So the first thing that we have to do is to convert from grams to moles of a substance. So we have 7-gram sample of magnesium oxide coming from the problem. So write 7 grams. Multiplied to the number of moles earlier that we have calculated. So in every 1 mole of magnesium oxide, there are 40.30 grams. Now let's cancel out the similar units, which is grams, and calculate. 7 times 1 divided by 40.30 grams will get an answer of 0.1737 moles of magnesium oxide. Now let's move on with letter B. How many particles of magnesium oxide are there in 7 grams of magnesium oxide? We have to convert from grams of a substance to its number of particles. And in able for us to do that, we're going to write the number of moles that we have calculated earlier. So that is 0.1737 moles of magnesium oxide multiplied to the Avogadro's number, in which it states that in every 1 mole, there are 6.022 times 10 raised to 23rd power particles. Now let's cancel out the similar units, which is the moles, and calculate. 17.37 moles times 6.022 times 10 raised to 23rd power divided by 1. And the answer would be 1.05 times 10 raised to 23rd power magnesium oxide particles. Okay. Now let's move on in getting the number of moles of oxygen in every 7-gram sample of magnesium oxide. Again, we're going to get the conversion from a mole of a compound to its component particles. Again, the component particles are the elements that made up the compound. And here we have in every 1 mole of magnesium oxide, there is 1 mole of oxygen. And now we compute. 0.1737 moles of magnesium oxide multiplied to, in every 1 mole of magnesium oxide, there is 1 mole of oxygen. So we're going to cancel out the similar units with each the mole and calculate 0.1737 times 1 divided by 1. We'll get an answer of 0.1737 moles of oxygen. Now we already got the molar mass, the number of moles, number of particles. Now let's move on with getting the number of ions of oxygen in every 7-gram sample of magnesium oxide. Able for us to do that, we're going to get the conversion from grams to moles to particles. So the first thing that we have to do is to write the number of moles in our sample, which is 7 grams, multiplied to the number of moles. So in every 1 mole of magnesium oxide, there are 40.30 grams. Then, we're getting the number of moles of oxygen in every 1 mole of magnesium oxide, which is both 1. Then, multiplied to the Avogadro's number, which is 6.022 times 10 raised to 23rd power oxygen ions over 1 mole of oxygen ions. Now cancel out the similar unit. We have grams for magnesium oxide, moles for magnesium oxide, and moles for oxygen. Now let's calculate. 7 times 1 times 1 times 6.022 times 10 raised to 23rd power oxygen ions divided by 40.30 grams times 1 times 1. And the answer would be 1.05 times 10 raised to 23rd power oxygen ions